So what does it mean for two lines to be parallel? Well, geometry already has a definition, right? Two lines are parallel if and only if they both lie in a plane and they never cross. So we need to come up with an algebra definition, but it has to mean the same thing, right? We aren't trying to come up with a new concept, just an algebra-based way of defining the concept that we already have. Right, so first, we don't have to worry about the in a plane part. Everything we're talking about here takes place in the flat Cartesian plane. Right, the part we really need to focus on is the never cross piece. Right, another way to think of never cross is they're going in the same direction. And that's something we can describe algebraically. In algebra, the direction the line is going, when it's up versus down, steep versus shallow, is defined by the slope. So we can say, using algebra terms, that two lines are parallel if and only if they have the same slope. Now, you notice I didn't put a period there, okay? Because we're not done, right? We're not done. Unfortunately, that's not quite going to be good enough. Think about this situation. Those two lines are still going in the same direction, but we definitely can't say that they still don't cross each other, right? So we have to add one more criterion to our definition to rule out this special case. So we're also going to require, let's say, if and only if they have the same slope and different y-intercepts. Those two rules together are enough to guarantee that our algebra definition gives the same results as the geometry definition.
So let's take a look at a quick example here and see how we can apply this definition. So I've got the equations of two lines here, and my question is, are these lines parallel? Well, we've got a rule we can use now, right? My rule says that to answer this question, I have to look at two things. I have to look at the slopes of the lines, and I have to look at the y-intercepts of the lines. And we know how to find those, right? I'm going to take these equations, I'm going to manipulate them a little bit, I'm going to put them into that slope-intercept form. And once I've got it there, it's easy, right? We'll just take the number in front of the x for the slope, the other number for the y-intercept, and we've got the numbers we need to compare. So, looking at the first equation, that's this one. I'm going to move the 3x and the 2 over to the right-hand side. So this becomes 4y equals minus 3x minus 2. Then we'll divide everything by 4. That gets the y by itself. And I do have one extra little thing I got to do now. That 2/4 needs to be reduced, right? I'm going to make that 1/2, and there's the slope-intercept form of the equation. All right, now let's do the same thing with the other one. I'm going to take that minus 6x minus 8y equals 1. And let's move the 6x over. Minus 8y equals 6x plus 1. And then we'll divide through by negative 8, just like we did with the 4 in the first equation. That gives me this one. Y equals negative 6/8 x minus 1/8. And again, I got a one little extra step. I got to simplify that fraction that's in the slope position. 6/8 negative 6/8 is negative 3/4. And now I've got what I need, right? I'm looking at these two equations, and I see that their slopes are the same. They're both negative 3/4. And their y-intercepts are different. One is negative 1/2, one is negative 1/8. So if you go back to our rule, because the slopes are the same and the y-intercepts are different, that tells me that these two lines are, in fact, parallel. So kind of looking ahead a little bit, the next goal for us is to kind of answer this same question about parallel lines, but thinking about perpendicular lines, right? How can we tell when we have the special case when two lines are perpendicular? We're going to have to do a little diversion first, right? In the next lecture, we're going to talk a little bit about how we can determine the angle between two lines, and then we'll use that to talk about when that angle is 90 degrees, which would make the lines perpendicular.